Okay, so in order to illustrate further the concepts that we have discovered in the case of ideal gas confined in a box with a partition in the middle, we're going to take advantage of another similar system, that's the ideal system of a capital N spins. Now, spin is a concept that appears naturally in the study of quantum mechanics, and there are a few things from other courses in physics that you will study in detail. We will just take in statistical physics as example systems in order to demonstrate our concepts. So, spin system is one of them. When you think about subatomic particles, for example, electrons, quantum physics tells us that these electrons have both wave-like and particle-like characteristics. And these characteristics can be uh, observed, for example, using diffraction experiments. Electrons show diffraction. That's a wave-like characteristic, and we will also show using photoelectric effect, for example, Einstein's photoelectric effect. Electrons also have particle-like characteristics. So electrons carry a charge with them, electrical charge E, and classically you can think of the spin as the spinning of a spherical particle around its axis. So it's created by the spinning of the electron, which gives you a spin angular momentum. Now, since you have a charge that is moving on a circular path as the electron spins around its axis, in electromagnetism, we find that if a charged particle moves on a circular loop, it's going to create a magnetic field around it, and there will be a corresponding magnetic moment that it will create. Okay, so these concepts will be studied in detail in electromagnetism and quantum mechanics. Now, when you think about the spin angular momentum of the electron, so I'm just considering the electron as a classical particle. Here is the spin angular momentum vector S, and if I take its projection onto the z-axis, quantum mechanical treatment gives me that the values of the angular momentum projection onto the z-axis are quantized. So it's either plus or minus h bar over 2. And we will assume that these spins are at fixed locations in a lattice, and the net spin may come from unpaired electrons, etc. So this is one example of a one-dimensional chain of spins. So this is a 1D chain of spins. And in total, we're going to consider capital N spin 1/2 particles. And why do we say 1/2? Because of this quantization on the z-axis, plus or minus h bar over 2. Each particle has a magnetic moment μ0, and these particles could be unpaired electrons, for example, or protons, etc. So there are many particles that have a spin. Now, S sub z, the z component of the spin angular momentum is quantized. It can only have two values, plus or minus h bar over 2. What is h bar? H bar is Planck's constant h divided by 2 pi. So H is Planck's constant. It is 6.63 10 to minus 34 joule seconds. The corresponding magnetic moment is given in units of a Bohr magneton, constant times a Bohr magneton. And what is a Bohr magneton? Mu B, a Bohr magneton is given as EH bar over twice mass of the electron, electron mass, the rest mass is 9.11 10 to minus 31 kilograms. So this is my Bohr magneton. Now you can see the electron charge E is a charge. It's going to be negative value if it's an electron, positive value if it's a proton. So the Bohr magneton can have a positive sign or negative sign depending on the sign of the charge. So for a spin 1/2 electron, we're going to have the mu electron is equal to minus mu 0, and for a proton we have mu proton is equal to plus mu 0. So we're going to consider the effect of sign of charge. So for electrons it's minus mu 0, for protons it's plus mu 0. Basically we find the direction of the magnetic moment using the right hand rule. So if you follow the spin direction with your right hand, it gives you the spin direction gives you this magnetic moment mu 0 magnetic moment will be in this direction given by the right hand rule, but because it's a negative charge, the actual direction of the magnetic moment will be basically this direction. So it's going to be minus mu 0. Okay, so we have to pay attention to the sign of the charge in order to determine the direction of the magnetic moment. And the other important thing is, in this ideal system of n spins, we're going to assume that these spins are at fixed positions. Okay, so another assumption here is spins are in fixed positions. For example, lattice sites. So you can see here I have a cubic lattice. There is a net spin for each atom, and each atom has a total number of unpaired electrons. So that gives me a net spin. So that could be a positive h bar over 2 or negative h bar over 2. And for magnetic moment, I have to consider basically plus sign or minus sign. So one thing I have to clarify here is that even though I have drawn this magnetic moment vector here like this, we're always referring to the component on the z-axis. So when we say the corresponding magnetic moment here, we should consider the z component. So this would be the magnetic moment mu 0 corresponding to this electron spin. So you don't consider the component on the spin angular momentum vector, but we always consider the component on the z-axis. And what defines z-axis, you may ask? It's the axis on which we apply an external magnetic field, actually. Okay. So what are the assumptions that we have about this ideal spin system? So we're going to assume that the average distance delta x between the spins is large enough for them to be considered as non-interacting. So average distance between neighboring spins. This is delta x, and this should be large enough to have non-interacting spins. So normally, since we have a magnetic moment that's due to these spins, the magnetic moments correspond to a magnetic field that is being created by the circulating charge, and this magnetic field will affect the spins of the neighboring atoms. So normally we should consider this, but since the effect of the magnetic field decreases rapidly with distance going from one spin to the other, if they are far away, if they are far enough, then this interaction between them can be neglected. Okay, so the important thing here is that the magnetic field B from neighboring spins is negligible. Now, in your basic physics classes, you have seen that if you put a magnetic moment inside a magnetic field, it tries to align with that field. So let me remind you that magnetic moment is the current I multiplied by area. So if you have a loop like this, you have a circulating charge Q on this loop. It's going to create a magnetic moment mu, like this, and A is the area of the current loop, and you're going to have this magnetic moment when it is placed inside a magnetic field at an angle with respect to the magnetic field. So if you have a magnetic field like this, external field, B external, and you put your magnetic moment mu at an angle with respect to this field, what happens to this magnetic moment? It's going to feel a torque so that it will eventually align with this magnetic field. Its energy, magnetostatic energy inside this magnetic field is minus mu dot product with the external magnetic field B, minus mu dot B. So when this energy of the system will be minimized when the magnetic moment aligns completely with the magnetic field, right? Okay, so because you have a circulating current that creates a magnetic field around it. So if you remember, the magnetic field due to a current was given by mu 0 I divided by 2 R, where R is the distance from the center of the loop. You're going to feel a magnetic field around this circulating current. So normally we have for a single wire, when you have current flowing through the wire, it's going to create a magnetic field around it. That's given by mu 0 I over 2 pi r. Its magnitude is mu 0 I divided by 2 pi r. Okay, so this a magnetic moment creates a magnetic field. A magnetic field interacts with a magnetic moment, and it will change the direction of the magnetic moment, etc. So basically what we're trying to say here is that this magnetic field from neighboring moments is negligible, and we can assume that these spins are non-interacting. Just as in the case of having n molecules of the ideal gas, we have assumed that there are no forces between molecules. They were non-interacting. Okay, so if I consider one spin, for one spin, I ask myself, what is the probability of having a spin quantum number 1/2? And what is the probability of having a spin quantum number -1/2? If there is no external magnetic field and there is no interaction between the spins, these two probabilities will be the same. It's analogous to ideal gas molecule. The probability of having it on the left-hand side is equal to the probability of having it on the right-hand side. It's 1/2 for a single molecule. Now, in this case, I call small n number of upspins, s is equal to 1/2, and n prime number of downspins, so that n plus n prime is equal to the total number of spins, and at equilibrium I have n is equal to n prime is equal to capital N over 2. So that will be the time average value of n is n over 2. Okay, so what is the probability of having all of these spins up or all of these spins down? That would be a very non-random configuration, and analogous to the case of having all gas molecules on the left or on the right due to a spontaneous fluctuation being very unlikely. We have in this situation also non-random fluctuations are rare. And there's one way to have this non-random or ordered situation, that's by external intervention. In the case of the ideal gas, we use the piston to push all the molecules to the left-hand side. Here, for example, we can most likely create this ordered situation due to an external magnetic field. Other than that, the probability of having this occur spontaneously is very, very small. So it's completely analogous to the case of having a system of n ideal gas molecules inside a container with an imaginary partition in the middle. Okay, so let's summarize what we have said here. We are considering spins as a model to study our statistical methods, and we're considering an ideal system of n spins. What is the meaning of ideal? Ideal means two things. They are at fixed locations. The spins are at fixed locations. The average distance between them is large enough that they are non-interacting, so they are free spins. And in the absence of an external magnetic field, they are free to point in the positive or negative direction. So you can have Sz is equal to plus h bar over 2 or minus h bar over 2 with equal probability for a given spin. Now, what is a spin? For example, if you think about the electron, you can consider this as a particle, classically as a particle, spherical particle with charge that is moving together with the electron. And this means you have a charge moving on a circular path. That means you have a current flowing on a circular path that creates a magnetic moment, current times area, and it also creates a circular loop. A current carrying loop also creates a magnetic field at its center, mu 0 I over 2r. If you have a wire, for example, using Ampere's law, you can find that you will have a magnetic field mu 0 I over 2 pi r. If you place a magnetic moment inside the magnetic field, its energy is minus, potential energy is minus mu dot b, which means, so this is my external field, which means that a magnetic moment will interact with an external magnetic field and will try to align itself with the external magnetic field. But since I have these magnetic moments mu separated from each other to a very large distance, so even though this creates a magnetic field around itself like this, field lines around itself like this, this intensity of the field is going to decay quite rapidly with distance between the moments, delta x. So if they are far enough, I can assume that the magnetic field has already died off and they are non-interacting, so they don't see a magnetic field. If there is no external magnetic field that I'm applying to the system of n spins, that means they are free to move in whichever direction they want. Now, some more details about results that you will see in quantum mechanics. This, what we are referring to as the spin is actually the z component of the spin, and the z component is basically the axis on which you apply an external magnetic field as a reference. So the spin can be, z component can be plus h bar over 2 or minus h bar over 2, where h is Planck's constant, 6.63 10 to minus 34 joule seconds. The corresponding magnetic moment we find using quantum mechanics, that is an integer number, is a constant times a Bohr magnetos, doesn't have to be an integer number. And it's the Bohr magneton is the unit of magnetic moment, is the quantum of magnetic moment, you can say, is EH bar over 2 ME. E is the charge. If it's electron, it's electron charge. ME is the mass of the electron, 9.11 10 to minus 31 kilograms. The magnetic moment corresponding to an electron or a proton spin will be different. The magnetic moment will be positive for the proton, negative for the electron. So you have to consider this when you are comparing the spins with moments. So the direction of the spin and the corresponding moment are opposite in the case of electrons. And these spins are assumed at fixed lattice locations. If this is a three-dimensional configuration, you can visualize it like this. And for statistical purposes, for one spin that is not interacting with any other neighboring spins or with an external field, probability of having 1/2 or -1/2 spin quantum number is 1/2. That means they are equally likely. It can point up or down. There is no preference. Just like having for a single ideal gas molecule on the left hand side or right hand side in the box with an imaginary partition in the middle. There is no preference, the probabilities are the same. So for capital N spins, the time averaged value of the number of up spins will be equal to the number of down spins, which is capital N over 2. If you want to observe a non-random configuration, you should apply an external magnetic field to align the spins, to align the moments with the magnetic field. Otherwise, those non-random fluctuations are quite rare.